Okay, so let's have a look at audio and speech and see how we can actually create our systems which will take an analog input, convert it into digital, and then give us an analog output again. Okay, so there is our lovely pure sine wave that we have. Obviously with speech, what we have is we have a harmonic, and then we have a fundamental frequency, and then we have harmonics on it. That gives the resonance around the sound. A typical bandwidth for speech is between 0 and 4 kilohertz. This is a traditional telephone line bandwidth. For audio, we need about 20 kilohertz. So our ears can only hear up to about 16 kilohertz, but normally we design our systems for up to 20 kilohertz. Okay. So Nyquist said that if we can sample at twice the highest frequency, then we can resurrect the signal back again exactly as it was. So that means that for our audio, we sample twice for every cycle, and then we should be able to reconstruct the signal back again. Okay, so it's twice the highest frequency. So in terms of speech, so we sample at 8 kilohertz, and 8 kilohertz gives us 125 microseconds is our sample time. For audio, we're at 20 kilohertz, so we need to sample once every 40,000 times per second, which gives us 25 microseconds. Okay, so we look at our maximum frequency that we have and we double it, and that gives us our sample rate. So this is what happens. We have our waveform, we apply a clock which is running at least twice the highest frequency of the signal. We then take a sample of that and we end up with a whole lot of samples. We then digitize that with an analog to digital converter, and we convert it into binary digits. On the other side, we take our binary digits, we put it into a digital to analog converter, and then we typically filter it, and that gives us our signal back. Okay, so if we have n bits, then obviously we have, the more bits that we have, the more levels that we have. So for n bits, we have 2 to the power of n different levels. So with 3 bits, we have 8 different levels. So then we would actually define them like this. Okay, and then when our waveform came in, if we sampled here, we define that as 0, 0, 0. If we sampled here, we would define that as 1, 0, 0. And if we sampled here, that is 1, 1, 1. So our maximum error is actually because we might get a sample right halfway in between. So our maximum error is what's called a quantization error. And that leads to noise called quantization noise. And that's equal to the full scale divided by 2 to the n. So that's that distance in there. And then the maximum error we're going to have is going to be half of that. So it's half plus or minus half of the full scale level divided by 2 to the power of n. That gives us that. Okay, so the quality of our digital system is defined by the signal to noise ratio. That's the signal to quantization noise ratio, and also the dynamic range. What's the smallest signal that we can actually represent? Obviously, if I had a really small signal here, it wouldn't actually be represented because we're never going outside the thresholds of the limits. So the dynamic range is the maximum voltage that we can apply, and Vmin is the minimum voltage that we can represent. We can go through the maths of that, but we actually find out that it's 6 times n, where n is the number of bits, decibels. And that gives us our basic dynamic range for the system. This is an example. So for 8 bits, we have 48 decibels ratio between the signal and the maximum signal and the smallest signal. If we go up to 16 bits, we move up to 96.33 decibels. As a ratio, the maximum is 65,000 times greater than the smallest amplitude. Okay, so for 16 bits, the actual smallest value that we can get is 65,000 times smaller than the largest. And it's really here that we see the quality of the audio, and that we need something like a 16 bits to really represent a proper dynamic range for audio. For the signal to noise ratio, it can be calculated that it's 1.76 plus 6.02 n decibels. So we can actually calculate that again. If we have 12 bits, then it's 74 decibels, and so on. Rather than doing a pure digital to analog to digital conversion, what we can do is use delta modulation. Delta modulation uses 1 bit at a time, and it tries to track the signal. So we can go up, 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 represented by 1, and then a 0, 0, 0, represented by down, and then up, down, down, down. So the zeros represent us going down, and the ones represent us going up. In that way, we can actually track the signal. And this is the circuitry that's involved in this. We need to sample at a higher frequency than we have now to be able to track the signal. But some say it gives a better quality of output. The problem that we have is that we can have what's called slope overload. Slope overload is where the signal changes too fast, such as here, and the tracker can't keep up with it. We also get what's called granular noise. If the signal isn't actually changing, then the counter will go up and down, up and down, up and down, and actually generate a signal on the output. The ways that we can overcome this is to actually use adaptive delta modulation, where we can increase the size of the step if we're not keeping up with the signal, and then decrease it again once we catch up with it. We can also use differential PCM. Differential PCM knows that the signal isn't going to change between certain regions. Nyquist defined that. So it will only move within a certain range from one sample to the next. So what we can do is that we can actually define a smaller amount of levels in between, and then look for a difference. So if we take one sample, and then the next one will be the difference between that sample and the next, which is the delta. The advantage with that is obviously it will give us very fine granular control, but the disadvantage is that, just like we've seen with motion video, we would have to take a sample every so often just in case we lost one of the deltas or one of the samples. Okay, so let's look at speech encoding and what's really different about speech. So some tests have been done to look at the signal to noise ratio and the dynamic range, and subjective and system tests have shown that 12 bits is the minimum that's really required for good quality speech. 8 bits really isn't enough, which means we've got 4,096 different quantization levels. And what it is that when we have loud speech and we add in the quantization error, then you don't really notice it because the speech is actually swamping the noise. But when it's soft and we add a quantization noise into it, then we can actually hear the noise in the system. So the noise itself is much more noticeable with low volumes. So what we do is that we make sure that we boost the lower signals, give them a boost up, but we do it to a lesser extent on the stronger end. So the response that we get is what's called companding, and companding takes our 12-bit code and then compands it into an 8-bit code using this logarithmic scale. The logarithmic scale is quite well balanced to what our ears would actually hear. There are two main companding schemes, mu law and A law. One is used typically in European systems and the other in the US. And they convert from 12 bits to 8 bits and make sure that we get a good boost to the signal around the zero areas, or the low volume areas around here. And on the other end we have an expander which takes the 8 bits and converts it back into 12. Okay, so we typically put it into a filter to make sure there's no high frequencies. What can happen is that if we do have high frequencies, they will fold back into our signal. So we make sure that we filter either at 4 kilohertz or 20 kilohertz for audio. Any frequencies that go above that in our signal will fold themselves back into the signal and give us distortion. We have our sampler running at twice the highest frequency. We put it to an analog to digital converter. We compand it. We send over with 64 kilobits per second. We're taking 8 samples, 8-bit samples and 8 kilohertz, so that gives us 64 kilobits per second. We expand it on the other end, we stick it into our 12-bit digital to analog converter, and we low-pass filter it again, and then we get our audio out on the other end. Okay, so this has been the traditional way that speech has been transmitted over a digital network. So one way we can actually do this is that we have what's called segmented or piecemeal. We can have a whole lot of segments, and then for each of the for each region we can have a different slope, and that will give us our A law or mu law. Some standards that there are around, so G711 defines the PCM standard, 64 kilobits per second, and the other ones are defined in things like adaptive PCM and so on. Okay, but our core is that it's 8 kilohertz, 4 kilohertz here into the samples, and then 64 kilobits per second is our base rate. We can then multiplex that up using time division multiplexing. With time division multiplexing we have a number of slots, and then we add our 64K streams into there, and then add those into an even bigger frame. And in this way we can send many different speech calls all at the same time. So if we take this, if there's 32 different slots and the time for each slot is 125 microseconds, we can actually determine the bit rate at 2.048 megabits per second, which is a fairly standard speed for the transmission of audio signals over a telecoms network. Okay, so that's been a basic introduction to audio and speech signals.